I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the variation of Fermi level in semiconductors with temperature and also with the variation in concentration. We have already discussed in this module, about the free electron theory, block theorem, chronic penny model, classification of materials, intrinsic semiconductors and extrinsic semiconductors. We have also derived expressions for carrier concentration. Now we are going to discuss in detail about the dependence of Fermi level on temperature as well as concentration. Means if the temperature varies, how does the Fermi level vary? And also with the concentration of impurities that are added. So let us see the brief outline how we are going to discuss. First, we will try to understand about extrinsic semiconductors. Then we will see what a Fermi level is exactly. And then how this Fermi level varies in N type semiconductors with the temperature. Means if the temperature varies, how do the Fermi level shift? And then we are going to see the variation of a Fermi level in N type semiconductors with concentration. If the concentration of the impurity atoms varies, how will the Fermi level vary? And in similar lines, we are going to see for P type semiconductors also. So what is the variation of Fermi level in P type semiconductors with the temperature and variation of Fermi level with concentration? So we are going to see for both N type and P type, we are going to discuss the variation of Fermi level with respect to temperature and also with respect to the concentration of donor atoms. Now in extrinsic semiconductor, first we are going to discuss about N type semiconductor. First we need to know what an N type semiconductor is. So when a pentavalent impurity atom like antimony or phosphorus or arsenic is added to a pure silicon crystal, 4 of its 5 valence electrons form covalent bonds with its neighboring silicon atoms. Means we are taking a semiconductor, a pure semiconductor we are taking, that is silicon. To that we are adding an impurity. So we are adding an impurity which is pentavalent. So after adding the impurity, what happens? Some of the silicon atoms are replaced by this pentavalent impurity. Suppose we are adding arsenic or phosphorus. So some of the silicon atoms are replaced by phosphorus. And now suppose if we have to look at the crystal structure after adding impurity. So this is the type of arrangement we have. The silicon atoms, which are semiconductors, they have 4 valence electrons. Each silicon atom has 4 valence electrons. And since phosphorus is a pentavalent impurity, so it will have 5 valence electrons. Now what we are seeing here is 4 of its 5 form covalent bonds with the neighboring silicon atoms. So 4 electrons are forming the covalent bond with neighboring atoms. These are the 4. Now what is happening to the 5th electron? The 5th electron of each impurity atom is loosely held with its parent atom. Parent atom here is the phosphorus atom. Okay. And it can be easily detached by supplying little amount of energy. So if I have to remove this electron, we need to supply energy. So 4 electrons are bound with covalent bonds and 1 electron is free for every phosphorus atom that is added. Now because of this, energy levels are introduced to all the 5th electrons of the impurity atom just below the bottom of the conduction band. We know the band structure, energy band diagram. In the valence band, we have the energies of all the valence electrons are represented by the valence bond. And this is the conduction band. The energies of all the free electrons are in the conduction band, are represented by conduction band. Now, what about these electrons, the fifth electrons and their energies? How do we represent them? They are represented by a donor level. This is the donor level. This is EC for conduction band. This is EV for valence band. Now, these levels are called donor levels, and the impurities added are called donor impurities. So, these pentavalent impurities, whatever we are adding, we are calling them as donor impurity. Why donor impurity? Because of 5 valence electrons. Silicon has 4 electrons, valence electrons. Phosphorus is giving 5 electrons. So 4 plus 5 is 9. It is always having 1 extra electron which it is ready to donate. So we are calling it as donor impurity. So at room temperatures or at temperatures very near to the room temperature, all the electrons in the donor level jump to the conduction band, because this is very near all the electrons which are there in the donor level. As soon as we supply little energy in the sense here even room temperature is enough to move these electrons into the conduction band. Because of this increase in temperature, all the electrons in the donor level will jump to the conduction band, and only a few electrons from the valence band will go to the conduction band. So when these electrons go to the conduction band, we have few holes. We have few holes that are left in the valence band. Now the electrons here are called the majority carriers and holes are the minority carriers, because electrons are more. The concentration of electrons is more than the holes. So that is why we call them electrons as the majority carriers and holes as the minority carriers. And now, as there are excess conducting electrons, the semiconductor that is formed after doping pentavalent impurities, we will call it as N type semiconductor. So now you know what an N type semiconductor is. We are doping it. Doping means the process of adding an impurity. So here the impurity we are adding is a pentavalent impurity. So when we are adding a pentavalent impurity, it is ready to donate 1 electron. So because of which it is forming an N type semiconductor. Now if we see the crystal structure, we have phosphorus, silicon. So phosphorus is surrounded by silicon atoms. All the 4 electrons are bonded by covalent bonds. 1 electron is free. And this electron is lying in the donor level. So this is the donor level. All the electrons that are not bonded or not forming the covalent bond, they are free. And as you increase the number of phosphorus atoms, there are more and more electrons and they lie in the donor level. So this is valence band, this is conduction band, and this is the donor level. It is due to the addition of pentavalent impurity. Now coming to the Fermi level. We need to understand Fermi level before we go to see how this Fermi level shifts. What is Fermi level? It is the highest energy level that an electron can occupy at absolute zero temperature. So this is the highest energy level, means above this level we do not find any electrons. So now if I say this is valence band and this is conduction band, we are talking for a semiconductor, a pure semiconductor. So the Fermi level is here. Means if I am talking about the Fermi level, means all levels below this are filled and you will not find any electrons above this. This is the highest energy level that is filled. And the Fermi level lies between the valence band and conduction band at absolute zero temperature. At absolute zero, the Fermi level lies exactly in between. Why? Because all the electrons are in the lowest energy state. So that is why the Fermi level lies in the center. Now, due to lack of sufficient energy at 0 Kelvin, we are talking that at 0 Kelvin, the Fermi level lies exactly at the center. What we are considering is it can be considered as a sea of fermions or electrons above which no electrons exist. Why we are talking about fermions here is actually Fermi level is coming from fermions. Fermions are nothing but subatomic particles. But in this context today, we are talking about electrons. So for electrons, there are no electrons above the Fermi level. If you are considering it like a sea. So above the sea level, you do not have any water. The same way we are talking about above the Fermi level, there is no electron. And this Fermi level changes as solids are heated. Means if you are supplying energy, thermal energy, when you are heating, you are supplying energy. So when they are heated, what happens? The Fermi level will change. It will shift. How it is going to shift, we are going to discuss. And also, when electrons are added or withdrawn, if you are adding in electrons, means if you are adding an impurity, a pentavalent impurity, which is a donor impurity, there are more number of electrons, you are adding electrons. Otherwise, in some cases, where there is a deficiency of electron, we are calling it as withdrawing the electron. So, in these cases also the Fermi level will change. Otherwise, at 0 Kelvin, it lies at the center. But with variation in temperature or with variation in the addition of impurity, this Fermi level will change. So, the position of the Fermi level in relation to the band energy levels is a crucial factor in determining the electrical properties. Now, whatever we are going to discuss with respect to Fermi level. Why Fermi level? Because this Fermi level determines many electrical properties. The more nearer it is to the conduction band, more the electrons can jump into the conduction band. So, when there are more electrons in the conduction band, means the conductivity is good. So, the level of occupancy determines the conductivity of different materials. So, if I have to talk about conductivity, I will check first where is the Fermi level. If the Fermi level is very near to the conduction band, it has good conductivity. Now, as the Fermi level approaches the conduction band, what is happening? It will be very easy for the electrons from the valence band to travel to the conduction band. So, why is the conductivity varying? With the variation in Fermi level. So, when the Fermi level approaches the conduction band, when it is very near to the conduction band, the electrons can jump very easily from valence band to conduction band. That is the reason the conductivity varies. Now we are going to see the expression for Fermi level. At very low temperatures, the number of electrons in the conduction band must be equal to the number of donor atoms. We are adding an impurity. So, in N type, we have added pentavalent impurity. So, whenever we are adding an impurity, for each atom we are adding, there is one extra electron which is ready to donate. So, these are the donor atoms we call. So, the number of donor atoms per unit volume will be equal to the number of electrons in the conduction band. So, we are going to take the two equations. One equation which we are getting for the number of electrons in the conduction band, it is given by this left hand side. And the second equation we are getting for the number of donor atoms on the right hand side, and we are going to equate them and then simplify. So, how we are going to simplify is, we will be just interchanging the terms. We have this term here, we will bring on to the right hand side, and the exponential term will take it on to the right hand side. So, what we get here is e power minus of EC plus EF by KBT, and this term when it comes here, EF plus ED by KBT. Now, if you are bringing this term to the right hand side, it goes to the denominator. So, we have ND by 2 into 2 pi ME KBT by H square power 3 by 2. Now we will rearrange these terms. E power minus EC plus EF. Actually, this is minus. So minus of minus we get plus EF. EF minus ED by KBT. You can simplify because EF plus EF gives us 2EF. So 2EF minus EC plus ED by KBT. If you are simplifying this term, what we get? 2EF minus EC plus ED by KBT is equal to ND by 2 into 2 pi ME KBT by H square power 3 by 2. Now we are going to take the logarithm and simplify. Taking logarithm on both the sides, we are going to use the expression exponential of log x is simply x. So here when you take logarithm of exponential 2EF minus EC plus ED by KBT, we are getting only x. So here we have 2EF minus EC plus ED by KBT is equal to logarithm of ND by 2 into 2 pi ME KBT by H square power 3 by 2. Now, how do we simplify this to get EF? Our motive is to get EF, the Fermi level. We are talking about Fermi level, how it is going to vary. So, to study how it is going to vary, we need an expression for EF and know its dependency on temperature. So, we are going to derive EF from here. So, we'll take this term also, minus of EC plus ED also onto the other side, and 2 goes to the denominator. So, we have EF is equal to EC plus ED by 2 plus KBT by 2 log ND by 2 into 2 pi ME KBT by H square power 3 by 2. This is at T greater than 0. So, only at a temperature T greater than 0, the electrons are shifting from the donor level to the conduction band, and then we are equating the number of electrons in the conduction band with the donor atoms that we are adding, concentration of donor atoms. Now, at T is equal to 0 Kelvin means if we are going to put this condition, the temperature at 0 Kelvin. So, what happens when we put for T is equal to 0, 0 into something is 0, so the whole term goes to 0. And we are left with EF is equal to EC plus ED by 2. So, this is what we are understanding now. EF lies between EC and ED. Okay. So, EF is equal to EC plus ED by 2 means EF lies between EC and ED. So, at T is equal to 0 Kelvin, Fermi level lies at the middle of donor level and conduction band. What we are trying to see now is, we have the valence band, the conduction band, this is the donor level. If I have to represent the energies, this is EC, this is ED, this is EV. So, what is the expression we got now? EF is equal to EC plus ED by 2. Means it lies exactly in between EC and ED. This is where we will have EF, the Fermi level. Now, as the temperature increases, what happens? The electrons in the donor level move to the conduction band. So, the electrons which are there here in the donor level, they move to the conduction band. And if you further increase the temperature, means if all the electrons in the donor atom are shifted to the conduction band, after that further you increase the temperature, then what happens? There will be breaking of covalent bonds now. Once you start increasing the temperature, what is happening? These atoms are getting ionized. The electrons are becoming free. They are shifting to the conduction band. But if you further increase the temperature, what happens? There will be breaking of covalent bonds. All the 4 electrons of the impurity atom which are bonded with the silicon atom are also breaking. Then what happens when the bonds are broken? Means some of the electrons from the valence band also shift to the conduction band. So, after the bonds are broken, electrons from valence band also shift to the conduction band. Now, as you increase the temperature more and more, the material starts behaving in an intrinsic manner. Means, the Fermi level now lies in the middle of the forbidden gap. If you see in an intrinsic semiconductor, we have seen that the Fermi level lies exactly in between the gap between the two, EC and EV. Now, as the number of electrons increases, what happens? The number of electrons in the conduction band will be equal to the number of holes in the valence band. Then slowly this Fermi level will shift towards the intrinsic semiconductor region, means exactly at the center. So therefore, as the temperature increases, the Fermi level lowers from EF is equal to EC plus ED by 2. Where is it now? It is in between EC and ED. Now, where it is going to come? It will come between EC and EV, which we call as the intrinsic level. It will come here. So, from here, slowly it will shift towards the intrinsic level at EF is equal to EC plus EV by 2. This is for a pure semiconductor, that is intrinsic semiconductor. The Fermi level lies exactly in between the energy gap, that is EC plus EV by 2. Now, we have added donors, and because of the extra electrons, the Fermi level has shifted towards the conduction band, and it lies exactly between the EC and ED. But with increase in temperature, more and more bonds being broken, and the concentration of electrons in the conduction band increases. So, from EF plus ED by 2, it shifts towards EC plus EV by 2. So, this is very important. When the temperature increases, the electrons in the donor level move into the conduction band. So, what happens? The Fermi level slightly shift upwards. So, with the increase of impurities, the Fermi level is shifting upwards, that is towards the conduction band. But if you are increasing the temperature further, what is happening? And also the whole concentration also increases, because more and more electrons from the valence band are also shifting to the conduction band. So there will be generation of holes in the valence band. So with the electrons, the whole concentration also increases, and it reaches again a concentration where N is equal to P. And here is the concentration of electrons in the conduction band, and P is the concentration of holes in the valence band. So initially the Fermi level is towards the conduction band, but as the temperature increases, the Fermi level is shifting towards the intrinsic semiconductor side when N is equal to P. So this is the diagram to understand. So initially, when you just start increase the temperature, only the electrons from the donor level shift to the conduction band. This is the donor level. This is the conduction band lowest energy level. So the Fermi level, which was lying in between the two before shifting the electrons, as more and more electrons move, what happens? This from here, it will come to the Fermi level. Fermi energy level, this is for a pure semiconductor. Where it lies exactly between EC and EV. This is EV and this is EC. So why is the shift occurring? This is due to the concentration of the atoms that are added. There is a donor level that is generated. Donor atoms are being transferred to the conduction band, and as the temperature increases, covalent bonds are also broken, and also electrons from the valence band are shifting to the conduction band, and the deficiency we are calling as holes. At one point of time, if the number of electrons in the conduction band is equal to the number of holes in the valence band, that is the condition where N is equal to P, what is happening? The Fermi level shifts towards the center, that is the intrinsic semiconductor position. Now, as the temperature increases, lowering of Fermi level, that is EF is equal to EC plus ED by 2 to intrinsic semiconductor level. EF is equal to EC plus EV by 2. This we have seen for temperature. Now we are going to see for concentration. Means if you increase the number of donor atoms, adding addition of impurities, if you are adding more and more number of atoms, concentration we are increasing. Concentration of donor atoms we are going to increase. So how will the Fermi level change? That is what we are going to discuss. Now if you see the energy level diagram, so this is EV, the lowest level in the valence band, and this is EF. This is for intrinsic level, means if at all it is a pure semiconductor, it lies exactly in between EC and EV. So this is the intrinsic level. Fermi level related to intrinsic semiconductor. Now with the donor atoms, what we have seen, when you are adding donor atoms, the Fermi level lies exactly between EC and ED. That is what we have seen here. Where is the Fermi level lying now? Because of the donor atoms we are adding, the Fermi level is at EC plus ED by 2, means it is here. The Fermi level is here. Okay. Now, if you are increasing the concentration, so what we are denoting here, ND. If the concentration of the donor atoms is 10 power 24 per volume, per meter cube. No, the number of donor atoms per unit volume we are talking about. So 10 power 24, the Fermi level is shifting like this. This is the Fermi level for ND is equal to 10 power 24. Now, if the concentration is 10 power 21, means slightly low. Concentration of the atoms is low. Then this is how the Fermi level is shifting. So what we understand here is, if the concentration of the atoms is more, this level shifts very slowly. And this is shifting fast. Where it will shift and come to the intrinsic level. That is what we have understood in temperature and what we are trying to understand for concentration also. From EF is equal to EC plus ED by 2, it comes to EC plus EV by 2. What is this position? Exactly at the center of EG. That is the extrinsic level. So from here, it shifts to EC plus EV by 2. And this is going to vary with the doping, if the concentration of atoms. So if it is highly doped, means if the concentration of atoms is more, 10 power 24, it is slow. Why? Because first the donor atoms have to go, and then only whatever energy we are supplying, that is used to break the bonds, and then electrons from the valence band will shift. So what we are trying to understand, how the Fermi level shifts with donor concentration is, as the number of donor atoms that we are adding increases, or the concentration of donor atom increases, the shift in the energy level becomes slow. Lesser the number of atoms, impurity atoms, the faster it will shift towards the intrinsic level. So as the donor concentration increases, the Fermi level lowers towards the intrinsic level. So this is what we are observing here. So if the concentration increases, it will shift, and we are seeing for two different concentrations. So if the concentration is more, when we are comparing with the lower one, here it is slow, here it is fast. Now we are going to understand for P type semiconductor. Whatever we have seen now is for an N type semiconductor. Now we are going to see the variation in Fermi level for P type semiconductor. So in P type semiconductor, how we are getting P type semiconductor? By adding a trivalent impurity. Trivalent means which has 3 valence electrons. We are adding a trivalent impurity like boron or gallium or aluminium. They are all belonging to third group. Now when you are adding a trivalent impurity to a pure semiconductor which has 4 valence electrons, what happens? These 3 electrons will form bonds with 3 of the valence electrons. Each impurity atom forms 3 covalent bonds. Why only 3 covalent bonds? Because we are adding a trivalent impurity which has only 3 valence electrons. So they form 3 covalent bonds with 3 neighboring atoms, with 3 of its neighboring atoms. And then there is a deficiency of electron to form the 4th covalent bond. There is no electron available to form the 4th bond and attain the closed shell configuration. What is this closed shell configuration? Is octet configuration we say. Octet means 8 electrons in the outermost orbit, which we call it as stable configuration. And the atom becomes stable. So whenever these atoms are brought together, they always try to form covalent bonds so that they attain the closed shell configuration. Now, because of the trivalent impurity, there are only 3 bonds that are formed and 1 electron is left without forming a bond. So what happens because of that? Energy levels are created to the electron deficiencies. Wherever there is an electron deficiency, we call it a hole. And corresponding to all these holes, there are energy levels that are created just at the top of the valence band. Means if you see the diagram, energy band diagram, this is the valence band, this is the conduction band, and above the valence band, there will be a level which we call it as the acceptor level. Means which is having deficiency of electrons. Acceptor. Why acceptor we are telling? It is always ready to accept an electron. If you give one more electron, so all the 4 bonds will be complete and it will attain closed shell configuration. So these levels we are calling them as acceptor level because they are ready to accept one electron. Now this is the diagram. This is the crystal structure where we will talk about boron in a P-type semiconductor. So there are only 3 electrons. So here there is no electron. 1, 2, 3. They are forming bonds with the 3 neighboring silicon atoms. But here for silicon, there is no electron here. So what is happening here? There is a hole, a deficiency of electrons. So there is no bond that is formed. So all these holes, where do they lie now? They lie in the acceptor level, which is denoted by EA. This is the acceptor level here. And where is the acceptor level lying? It lies just above the valence band because it is ready to accept the electrons which are going to become free from the valence band. So now at T is equal to 0 Kelvin, this is the scenario. Whatever atoms we have added, all the electrons which are bonded and then the holes which are deficiency of electrons, they are in the level above the valence band, which we call it as the acceptor level. Now at room temperature, what happens? For this atom where there is an acceptor level, many electrons nearer to the top of the valence bond jump into the acceptor level. If you slightly increase the temperature, means even at room temperature, electrons from the valence band now move to the acceptor level because it is ready to accept the electrons which are becoming free. In previous case, they used to go to the conduction band. Now, before the conduction band, there is one more level which we are calling as the acceptor level. So, these electrons first now jump to the acceptor level and only a few electrons jump to the conduction band. Okay, if you are further increasing the temperature, then electrons will move to the conduction band. So what happens here? There will be holes in the valence band. But because of this acceptor level, the number of holes is always more than the number of electrons. So the majority charge carriers are holes in the valence band and the minority charge carriers are electrons. There are few electrons in the conduction band. So we are calling them as minority charge carriers. Whereas the holes which are there in the valence band, they are the majority carriers. Now, as there are excess number of holes, that is why we are calling them as majority carriers. The semiconductor that is formed by adding a trivalent impurity, if they're asking you to define what a P-type semiconductor is. So, this is how you have to define the semiconductor formed after doping trivalent impurities to a pure semiconductor. We call it as P-type semiconductor. And the impurities, we are calling them as acceptor impurities because they are ready to accept the electrons. Now let us derive the expression first for Fermi level and then discuss how the Fermi level is going to shift. We have already seen the expression. Only difference here is we are talking in terms of the number of holes in the valence band. whatever, if you have understood how we have derived expression for Fermi level in case of N type, it is very similar. Only thing here is electrons are replaced by the holes, because there we were talking about the donor energy level. Here we will talk in terms of acceptor energy level. That is the difference between the previous derivation for Fermi level and this derivation. So let us now see the expression. So at very low temperature, when electron hole pairs are generated, how are the electron hole pairs generated? Due to the breaking of bonds. So the number of holes in the valence band must be equal to the number of acceptor atoms per unit volume. So there we were talking in terms of electrons. So here we are talking in terms of holes. The number of holes in the valence band depends or must be equal to the number of acceptor atoms. So the number of holes is given by 2 into 2 pi mp. mp here represents the effective mass of hole. mp star means it is the effective mass. Effective mass of hole. And EV here represents the valence band. EV, energy level, top level of valence band, topmost energy level of valence band. These two terms we should know. And EA is the acceptor energy level. EA is the acceptor energy level. So once you write this expression and equate, the rest of the things are simple mathematical simplification. We are going to take this exponential term onto the left and bring this term onto the right and then simplify. So what we have here, e power minus EF plus EV by kBT by e power EF minus EA by kBT. The base is the same, so we can combine the powers. This goes to the numerator, it will be, the sign changes. So minus EF plus EV minus EF plus EA, because this plus EF, when it goes to the numerator it becomes minus EF, minus EA when it comes to the numerator it becomes plus EA. So here we have minus EF and minus EF, so we get minus 2 EF and EV plus EA. So e power minus 2 EF plus EV plus EA by 2 kBT, and the right hand side remains the same. So Na upon 2 into 2 pi mp kBT by h square power 3 by 2. Now we are going to take logarithm on both the sides like we have done in the previous case. So by taking the logarithm on both the sides, what we get? Exponential of log x is x. And what is our x? This is our x. Minus 2f plus EV plus EA by kBT is equal to log Na by 2 into 2 pi mp kBT by h square power 3 by 2 on taking the logarithm on both the sides. Now I take kBT also onto the other side. So if we are taking kBT, it goes to the numerator. So minus 2 EF plus EV plus EA is equal to kBT log Na by 2 into 2 pi mp kBT by h square power 3 by 2. Now if we want to write the expression for EF, we will take EV plus EA also onto the other side. Or we'll take 2EF onto this side, it will become plus, kBT onto this side, it will become minus. Either way you can think. So EF will be equal to what? EV plus EA by 2 minus kBT by 2 log Na by 2 into 2 pi mp kBT by h square power 3 by 2. So this will be a general expression for EF at any temperature greater than 0 Kelvin. So we are going to use this expression for finding the Fermi level at any temperature T greater than 0 Kelvin. Now if you are going to put the condition T is equal to 0 Kelvin at temperature equal to 0 Kelvin. If you substitute for T is equal to 0, 0 into something, the whole term goes to 0. And then EF will be equal to EV plus EA by 2. So you need to understand the terms here. In case of EF, we were talking in terms of the conduction band and the donor level. Here, because it is the holes, we are talking in terms of the valence band and the acceptor level. So EF is equal to EV plus EA by 2. It means EF lies in between EV and EA. The average it is shown. So EF lies between EV and EA. So in case of P-type semiconductor, where is the Fermi level? It lies between EV and EA. Now as the temperature increases, the electrons in the valence band move into the acceptor level, leaving holes in the valence band. So first, which electrons are going to shift? This is the conduction band. This is the valence band. This is the acceptor level. This we are calling as EC, EV, and this is EA. There are deficiencies here. There are holes here. So when we increase the temperature, what happens? Some of the bonds are broken and the electrons from the valence band go to the acceptor level. They are filling in these gaps. They are nothing but deficiency. So the Fermi level shift downwards and lies slightly above the valence band. So where will be the Fermi level now? The Fermi level will be in between EA and EV. Now if further increase in temperature is done, means if you are increasing the temperature further, more and more bonds are broken. So what happens? It reaches the concentration of N is equal to P. Means the number of, now initially the number of holes are more than the number of electrons. But as we increase the temperature, more and more bonds are broken, more and more electrons after filling the acceptor level, they shift into the conduction band. Slowly a stage is reached where N is equal to P. So what happens then? The Fermi level increases and reaches to intrinsic level. So from here, the Fermi level will be shifting towards the intrinsic level. So from here, it will shift towards the intrinsic level. So we'll quickly recollect what we have seen. At T is equal to 0, Fermi level is at the middle. Middle of what? Valence band and acceptor level. But as temperature increases, what happens? Electrons in the valence band move to the acceptor energy level. And if there is further increase in temperature, what happens? All acceptor atoms get ionized, and then electron hole pairs are generated due to breaking of bonds. So initially it is only due to the donor atoms. The electrons are moving towards the acceptor level. Now because of further increase in temperature, there are bonds that are broken, because of which there are electrons moving into the conduction band. So because of that, what happens? The material behaves in an intrinsic manner where the Fermi level is at the middle. In an intrinsic semiconductor, where is the Fermi level? It lies exactly in the middle of the energy gap, that is in between EC and ED. So what we are seeing here is the Fermi level which is at EV plus EA by 2. In P type, as the temperature increases, the Fermi level is shifting towards EC plus EV by 2. So this is what we are trying to understand, how the Fermi level shifts with increase in temperature. So as the temperature increases, the Fermi level shifts from EV plus EA by 2 to EC plus EV by 2. That is the same case with intrinsic semiconductor. Now if I have to show the diagram with temperature. Conduction band, valence band, this is EC, this is EV, there is a acceptor level which is EA, and because of which the Fermi level is lying here, EF. So this position we are calling as EF is equal to EV plus EA by 2. But because of the increase in temperature, more and more electron hole pairs are generated. The Fermi level slightly shifts towards the intrinsic level like this. This is the intrinsic level. So what is this here? EF is equal to EC plus EV by 2. This is what we have understood. So how is the Fermi level shifting with increase in temperature? So as the temperature increases, the rising of the Fermi level EF is equal to EV plus EA by 2 to intrinsic level depending upon doping. We are now going to see the shift in Fermi level with increase in concentration of the doped atoms. So when we are doping it with a trivalent impurity, because of which there is an acceptor level. So now because of the acceptor atoms, the Fermi level lies between what? EV and EA. Okay. So the Fermi level is here now. It is here between EV and EA. Now as the concentration increases, means the concentration of atoms here is 10 power 21 and the concentration of atoms here is 10 power 24. So we are trying to compare with respect to concentration. So if the concentration of the atoms is more, the shift in Fermi level is slow. When the concentration of atoms is less, the shift in Fermi level is fast. How is it shifting? It is shifting from a level EF is equal to EV plus EA by 2. From here, it is shifting to this level. EF is equal to EC plus EV by 2. So how it is shifting with concentration? That is what we are trying to understand. So with increasing concentration, this shift is slow. So it is slow in case of highly doped material. Means when the concentration of atoms is more, the shift in Fermi level is slow. So as the acceptor concentration increases, the Fermi level increases and reaches towards the intrinsic level. That is what we are talking in terms of EC plus EV by 2. So let us now try to compare all the three. If we put together, the picture becomes very clear. So this is for an intrinsic semiconductor. This situation is for an intrinsic semiconductor. So what is this? This is the valence band. This is the conduction band. So we are talking, this is EC, the lowest level in the conduction band. This is EV, the topmost level in the valence band. Now when you are having an intrinsic semiconductor, the number of holes is always equal to the number of electrons. So the the Fermi level lies exactly in between the energy gap, that is in between EC and EV. This is the Fermi level for intrinsic semiconductor. So the Fermi level lies exactly in between. Now when we see N type, in N type we are adding a pentavalent impurity. Because of that there are donor levels that are generated. There are more and more number of electrons. So the concentration of electrons is more than the concentration of holes. So that is what you observe here. These are the electrons in the conduction band. This is the conduction band. And these are the holes in the valence band. So you can visualize the number of electrons in the conduction band is more than the number of holes in the valence band. So what happened? The Fermi level shifts towards the conduction band. So where is the Fermi level now? It is shifting towards the conduction band. Means we have a donor level here and this EF lies between EC and ED. This is what we have seen the expression. So what you need to understand is the Fermi level shifts towards the conduction band in N type. Now this is for P type. So in P type what we have, we are adding a trivalent impurity. There are deficiency of electrons and the deficiency of electrons we are calling them as holes. And due to that we have a acceptor level that is formed here. This is the acceptor level. And the Fermi level lies exactly in between EV and EA. So where is the Fermi level shifting now? Towards the valence band. In case of N type, it shifts towards the conduction band. And in case of P type, it shifts towards the valence band. Here it lies between EC and ED, the conduction band and the donor level. Here it lies between the valence band and the acceptor level. So here for this we are writing EF is equal to EV plus EA by 2. And in this case we are writing EF is equal to EC plus ED by 2. But what is happening as the temperature increases? In this case also it will slowly shift towards the intrinsic level, and here also it will shift towards the intrinsic level. It will come up like this and reach the center position in the energy gap. Here also it will reach in the center. So we are going to see it with the help of a simulation. So now if you see when the temperature is low, if you see when the temperature is here, so the Fermi level will be at the intrinsic level. But as the temperature increases, you see the cursor moving here. What is happening to the Fermi level? The Fermi level is shifting. So the whole lecture we were talking about how do the Fermi level vary. So initially for a N-type semiconductor, it is near the conduction band. But with increase in temperature, it is shifting towards the intrinsic level. And for a P-type, it is near to the acceptor level, but with increase in temperature, it is shifting towards the intrinsic level. That is what we are going to try to see with the increase in temperature, how the Fermi level shifts. So if you want more details regarding this Fermi level or any clarification regarding the derivations, you can refer to P.K. Palaniswamy Engineering Physics or Engineering Physics by Gaur and Gupta. Thank you. See you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.